Good evening, everyone. Today, I, YUVANSH, and my group members, MADHAV, Aryan, and ARNAV, would like to present AIML for process improvement in manufacturing, a case in starter Ringgear manufacturing industry. This is a minor project presentation. Now, I would like Madhav to elaborate further.
So, in this project, we explored how artificial intelligence and machine learning contribute to the transformation of modern manufacturing under Industry 4.0. AI and ML enable manufacturing systems to become predictive, adaptive, and data-driven. Our focus is to understand how these technologies can conceptually enhance the production of starter ring gears. So, onto the problem context. Gear manufacturing today still face several operational challenges, which includes frequent unplanned downtime due to tool wear, quality inconsistency in heat treatment and finishing, and the underutilization of machine-level sensor data all contribute to inefficiencies. These recurring issues demonstrate the need for predictive and intelligent manufacturing systems. So, how AIML contribute to Industry 4.0? Industry 4.0 integrates cyber-physical systems, IoT, AIML, and automation to create intelligent factories. AI and ML form the key intelligence layer. Machines learn from data, predictive failures, and optimize process in real time. Our project aligned directly with this by examining AI ML possibilities for smarter gear manufacturing. So, what are the research objectives? Our research has four objectives. First, to identify inefficiencies within the current manufacturing process. Second, to analyze how AI/ML can address these issues. Third, to design a theoretical framework for predictive and efficient manufacturing. And finally, to integrate academic insights with on-ground observation using a structured analytical approach. So, on to you, Vansh.
Thank you, Madhav. So, on to the methodology. Our study uses a qualitative exploratory single case study design to understand the manufacturing process in depth. We use two sources of data, basically. A secondary scoping literature review to build theoretical grounding, and a primary non-participant observational visit to study the actual workflow at the plant. The analysis was as such, as is pain points in 2B model, mapping several observed inefficiencies to draw the solutions necessary. Coming on to the hierarchical analytical framework. So basically, the framework that we adopted was on 3 levels. At the material level, AI can support decisions related to hardness, surface quality, etc. At the process level, it can optimize operations like hobbing and induction hardening. And at the system level, AI supports factory-wide optimization, such as scheduling, maintenance, and decision support systems. Coming on to the as-is process flow. This is the current manufacturing process for starter ring gears, covering welding, hobbing, induction hardening, rebore, deburring, and inspection. Our observation highlighted that the process is largely linear or reactive process instead of being proactive. Many steps exist to fix defects after they occur rather than preventing them proactively. This gives rise to the pain points.
So, through our qualitative observation, we identified 3 major pain points. The first is a reactive process philosophy highlighted by the presence of steps like rebore and deburring, which corrects defects after they occur. The second is unplanned downtime risk, especially in hobbing, where tool changes are based on fixed schedules, leading to unexpected failures. The third is data-rich but knowledge-poor environment. Machines like induction hardening unit collect sensor data, but this information is used only for alarms, not for predictive analysis. So now, our proposed 2B theoretical frameworks addresses these pain points. We designed these 2B frameworks, which are framework move the system from reactive to proactive through AIML modules targeting maintenance, quality, optimization, and energy. Our modules includes 4 key modules with the help of our research paper, which includes predictive maintenance, using modules to forecast tool wear and prevent downtime. Quality prediction, using regression modules to forecast deviation in tool profile and surface finish. Process optimization, which with the help of reinforcement learning enables real-time parameter turning in hobbing and induction hardening. And the last is energy efficiency, which is AI-driven control, which help optimize furnace operation, supporting sustainability and cost reduction. Now the next part is for Arnav.
Thank you, Aryan. Methodological limitation and scope. In this way, our research is qualitative and not observational, not an implementation project. We do not have access to live production data, therefore, we did not perform empirical validation. The outcomes are conceptual in nature and a theoretical framework showing how AI/ML could be applied to the addressed observed efficiency. Data challenges. This slide highlights the key data issues that slow down AI adoption: data soils, inconsistency, infrastructure, poor data quality, and lack of historical data. Solving these is essentially before implementing AI. In AI/ML adoption roadmap, the roadmap outlines a realistic approach to AI adoption, starting with data readiness, moving through pilot projects, building workforce capability, and finally scaling to a full intelligent manufacturing environment. This step-by-step development is essential to ensure sustainable and efficient transformation. The conclusion for our presentation is to conclude our project demonstrates how AI/ML can conceptually address core efficiency in gear manufacturing under Industry 4.0. We have proposed a theoretical predictive model built on both academic literature and real-world observation. This lays the foundation for future studies that can validate and implement these solutions using live industrial data. Thank you.
Thank you.
Thank you.
Thank you.